Let's just go through a few basic things about a simple decision tree. How did we do these splits? As you might expect, we used the training data. How do we define what to predict for a future case? We do that as well based on the training data. We look at which leaf an observation ends up in. So if the word pilot is there in this simple tree, an observation will end up in this leaf over here. And what will we do now? We need to make a prediction about it based on the training data. We can predict a 0 or 1. We can predict pilot error or not error. And if we did that in this case, we would predict pilot error because 97% of the examples in the training data in this leaf are indeed pilot error. So that would be the best thing to predict. Or we can predict probabilities. We think there's a 97% probability that this particular accident was due to pilot error. Let's talk about how we made this split in the first place. At the very beginning, when you hopefully decided to use the word pilot to make this split, how did you make that decision? What you were probably doing, whether you realized it or not, is you were trying to minimize a loss function or maximize some other kind of function. For example, maximize accuracy. You reckoned if I split according to pilot and then I make guesses according to pilot, I'm going to have a certain accuracy. Let's see how that would work in this particular case. What would your accuracy be based on this training data? Well, for the cases that end up down here in this leaf, you're going to predict for all of them that it is pilot error. And for 97% of them, it will be pilot error. So your accuracy is 97% on 54% of the data. On the other hand, for the examples that end up in this leaf over here, what are you going to predict? Well, only 47% of them are due to pilot error, and therefore, presumably you will predict not pilot error. What is your accuracy in that case? 53% are not due to pilot error, and that's what you predict. So you get it right 53% of the time, and that is on 46% of the data. So your overall accuracy is going to be 97.97 times 0.54 plus 0.53 times 0.46. Whereas had you not made any splits at all, and you were still at the top level, the only thing you could do at the top level was to predict that every accident is due to pilot error, in which case your accuracy will be 0.74. If you do the calculation, you will find that the average accuracy after the split is greater than the accuracy before the split, and therefore if you were a computer making a decision tree, you would say, I should make the split. Well, I thought I might as well just do the maths. This is what I got. I hope I tapped in the numbers correctly. The accuracy before the split is 0.74. The accuracy after the split is 0.77, so the accuracy increased. We prefer to talk about loss functions, things which we try to get smaller. So the easiest way to make a loss function here is just to think about 1 minus accuracy, which was 0.26 and is now 0.23. So the loss function has reduced by a fairly massive amount as a result of this one split. Fine. Is accuracy a good loss function? I hope you remember that accuracy is a dreadful loss function because it essentially can have a derivative of 0. So if you try to minimize it with gradient descent, you will never manage. How could we see that here? Well, imagine if after making this split over here, the proportion of pilots with pilot error was not 0.47, but was something like 0.51. Now in this particular case, over here you would predict pilot error. Over here you would also predict pilot error because the probability is greater than 0.5, so you're best off predicting pilot error. You would predict pilot error in both cases, and therefore there would be no improvement whatsoever in accuracy because before the split you're predicting every accident to be pilot error, and you're doing the same after the split. And yet you can see it would definitely be worth making this split because we have separated the data into two different buckets, and at the very least there's now a good possibility that when you split this leaf over here into another two leaves, you're going to find that one of the leaves has a probability of less than 0.5. If accuracy is a dreadful loss function to use for splitting decision trees, because sometimes you just won't make any splits whatsoever, what is a good function to use for making decisions when splitting decision trees? Believe it or not, one of them is mean square error. There's nothing at all wrong with using that. It tends to work quite well. Another one, which was used by the original people that created decision trees, Bremen, Friedman, Olshan and Stone, is something they called Gini, although that shouldn't be confused with other measures called Gini, which is simply equal to p times 1 minus p in each node, where p refers to this 0.97 over there or the 0.47 over there. It ends up working quite well. In fact, I think you'll find that for a classification task it's identical to the mean square error. So we are building our model, and the first thing we do is we make a split with which we try to minimize a loss function, and then we make another split in order to minimize the loss function further, and then another split, and then another split. Each time we take a step trying to minimize the loss function. I hope this sounds very familiar to you, and I hope that you're thinking it feels quite a lot like gradient descent. What we did in gradient descent was to use the derivative to try and minimize the loss function, and we took lots of steps bit by bit in a particular direction. Here once again we're trying to minimize the loss function and we're taking steps. What's the difference? The difference is the function that we use each time when we add an extra step. In the case of gradient descent on linear regression, the function that we used when we added each step was a little mini linear model. We added a little bit onto each beta. That is essentially a step using a linear model, albeit a linear model with very small coefficients, because the coefficients are just the step taken in each direction. Over here, again, we're taking steps, but this time the steps we're taking are done by splitting the data. If accuracy is a dreadful loss function to use for splitting decision trees, because sometimes you just won't make any splits whatsoever, what is a good function to use for making decisions when splitting decision trees? Well, believe it or not, one of them is mean square error. There's nothing at all wrong with using that. It tends to work quite well. Another one, which was used by the original people that created decision trees, Bremen, Friedman, Olshan and Stone, is something they called Gini, although that shouldn't be confused with other measures called Gini, which is simply equal to p times 1 minus p in each node, where p refers to this 0.97 over there or the 0.47 over there. It ends up working quite well. In fact, I think you'll find that for a classification task it's identical to the mean square error.